In this video, we're going to look at some integration rules, specifically the sum and difference rule, constant multiple rule, the rule if the limits are equal, and the rule for a continued interval. If you'd like to skip to any of those sections, there will be links to the times in the description. The first one we're going to look at is the sum and difference rule, and basically two rules here. So if I have the integral from a to b of f of x plus g of x dx, where I'm adding the two functions in the integrand, that's the same as doing the integral from a to b of f of x and the integral from a to b of g of x and adding those together. Similarly, if I have the integral from a to b of f of x minus g of x dx, that will equal the integral from a to b of f of x minus the integral from a to b of g of x. And this should not be surprising. Basically what's happening is this. I have two things, and I'll make them relatively simple. I have some function f, which gives me something. We'll just say, okay, it's a rectangle, some constant. And I have some function g, a line, on top of it. And I can basically take the area of the first, the area of the second, and add them up, and it will be the area of the whole thing. So that's basically what's happening. Similarly, with the subtraction, I take the area of one and take away the area, the signed area, the integral of the other. So let's see a little example. And in this one, if I were trying to graph this function, the integrand, directly, it's going to look sort of like this, which is a mess. And I don't necessarily have, off the top of my head, a single area formula for this to try to evaluate that geometrically. But I can split this up, and there's a few options. I'm going to split it up as this piece and this piece. And so I'll look at it as the integral from -4 to 4 of x plus 4 dx plus the integral from -4 to 4 of the square root of 16 minus x squared dx. And this right here forms a triangle with base from -4 to 4 being 8 units long. The height over here occurs when I put the upper limit into the integrand, and that's going to be 8. And so this signed area is 1/2 8 times 8, which will be 32. This right here is a semicircle with radius 4. And so the area of this is going to be 1/2 pi times 4 squared, which is going to be 8 pi. And that means that this whole integral is going to be 32 plus 8 pi. Now you may wonder, how do we get this from this shape? And it's relatively simple. The triangle I can see right here. This, it's not a half circle, it's sort of stretched as it is, but the area of this remaining piece will equal the area here, because basically I can sort of look at this, all these heights here will be equal to the corresponding heights here. It's just skewed a little bit. So the areas, if this sort of dropped down, would be exactly equal to the area of this half circle. Alright, the constant multiple rule. So in this case, if I have the integral from a to b of some constant times f of x dx, that will be the same thing as that constant times the integral from a to b of f of x dx. And the reason for this, so because I'm basically multiplying every height by k. If this if this here formed a rectangle, then this is going to form a rectangle that's k times taller, and so as an area times k. And that should be obvious for a rectangle, but it works for any shape, because if I sort of scale it in one direction, it's going to multiply that scalar to the area directly, not any other squared or anything in there. So let's see an example of this. So in this case, I have this shape. Now, this graph will look something like this. This being at -3, this being at +3, this y-intercept being up here at 15. And I'm only finding the integral from -3 to 0. And so in here, all I need to do is look at this as 5 times the integral from -3 to 0 of this half circle. I'm only doing half of this half circle, so this area here will be 1/4 of pi times 3 squared, which is going to be 9 pi over 4. But I still have to multiply it by 5, which would get me 45 pi over 4. All right, the next rule is this. If I have equal upper and lower limits of integration, if I have the integral from a to a of f of x dx, then it's going to equal, I just don't need that little arrow, it'll equal 0, because regardless of what my curve looks like, if I'm only going from a to a, it may have height, positive or negative, but it'll have no width, so it has no area. An example of this is right here. It's a mess in here. I haven't actually shown a video in this sort of sequence yet of how to find the integral of a quadratic or the integral of a sine function. We'll get there in about 4 or 5 videos. But it doesn't matter because I'm going from pi to pi, so this will equal 0. Now, let me go back for a second. I messed up when I made this and forgot to put one of my rules up here, so I'll just shove that in right here. I apologize for the mess here. So what if I have switched limits? And to answer that question, if I have the integral from b to a of f of x dx, I can flip those limits by changing the sign. Negative integral from a to b. And that should make sense because basically what's happening is if I had, let's just say, a rectangle, so I had, the integrand being a constant, and I went from here to here, the width is like it's positive. But if I flipped them, then instead of going from here to here, I'm going from here to here, which is decreasing, and it's like the width would be negative. Again, I'm saying like, widths are always positive, areas are always positive. Integrals take areas and add possibly a sign to them, whether they're positive or negative above or below the x-axis, or whether I am going from a larger number to a smaller number. And I'll toss in a little example here, so I'll just call this example 3b. And I want to evaluate the integral. Let's do the integral from, let's make it easy, 5 to 2 of 2 dx. And this is a horizontal line, so let me graph that. And if I go from 5 to 2, so I have a limit here at 5, a limit here at 2, and I end up getting this rectangular region that's above the x-axis. And so I know that the integral from 2 to 5, going lower limit, upper limit of 2 dx, is going to be the area of this, which is a 3 by 2 rectangle, which is 6. But since I'm not going from 2 to 5, I'm going from 5 to 2, this integral will be negative 6. All right, final rule, continued interval. So if I have the integral from a to b of f of x dx, and add on to it the integral from b to c of f of x dx, that's going to actually equal the integral from a to c of f of x dx. So that should make some sense. Let me put up a, b, and c. And I'm going to have these increasing. They don't need to actually be increasing. B could be outside of a and c. A could be bigger than c. There's many things that could happen here. But if I have a constant function from a to b, and then a triangle from b to c, you can clearly see that this integral can easily be found by finding this area from a to b and this area from b to c and just adding it together. Now, one of the most common ways that I've seen on the AP test for them to ask for this is giving a problem where they give you the integrals already. And so in here, I'm given the integral from 1 to 7 of f of x dx. I'm given the integral from 5 to 7 of f of x dx. And I want to find the integral from 1 to 5. So here's the problem. I'm not given from 1 to 5. I need to work my way there. So I know that integral from 1 to 5 of f of x dx will equal the integral from 1 to 7. I want to start at 1, and I can only go from 1 to 7 of f of x dx. And I'm going to be able to get the integral from 7 to 5. So I went from 1 to 7 and then 7 to 5. And that's going to be the same as going from 1 to 5. Now, I'm not given the integral from 7 to 5. I'm given the integral from 5 to 7. So when I flip these, this remains unchanged. But this will change signs. And now I can just substitute in the values. The integral from 1 to 7 is 9. Integral from 5 to 7 is 3, and my answer is 6. I hope this helped out. Feel free to comment below if you do have any questions.